Okay, Zoli, the stage is yours.
Thank you. I'm Zoltán Kolarovszki. I'm a junior research fellow at Wigner Research Center for Physics, and I'm also a PhD student at Eötvös Loránd University, hopefully not for long. And today I will talk about line search in CV, continuous variable quantum circuits. I chose this particular topic because it connects really well with Péter Rakita's presentation this morning, and also with Péter Kovács's presentation. He talked about photonic quantum circuits. Okay, so this will be, I will escort you through a journey which I did like half a year ago. I will start with discussing parameter shift rules, and then I want to determine parameter shift rules for continuous variable quantum computing. And then I ask the question, is it really good if we try to apply parameter shift rules? Is there anything better? And then I will discuss line search strategy, which I have fine. Yes, parameter shift rules. What are parameter shift rules? For introducing them, first I will have to talk about variational quantum circuits. A variational quantum circuit consists of an initial state, possibly depending on some data x, but it's optional. A quantum circuit, which is parameterized by some free parameters, theta, and a set of observables to be measured. And we calculate or estimate at least the expectation values of these observables. And from the observables, generally we calculate a loss function, and the goal usually is to minimize the loss function by tuning the theta free parameters somehow, usually by gradient-based methods, but you can also use gradient-free method. Okay, so here is the circuit. So if it was too much, so here you start with the, here you start with your initial state I mentioned. It enters this quantum circuit, which is parameterized by some theta. You choose some random parameters initially, and then you measure these observables. You can calculate these expectation values, this fj, which I mentioned. You calculate the loss function, and then according to the gradient of the loss function, you adjust the parameters. But how do you determine these gradients efficiently? This is like the core question of this presentation or this talk. There are multiple pressing issues in quantum machine learning, but this is the one I will talk about now. Okay, so what are the options? We have several options, at least three. One is symbolic differentiation. So I'm talking about, it's a conventional computer, sorry. A traditional computer. On a traditional computer, you can do symbolic differentiation using some symbolic computer algebra package. You can do automatic differentiation. It is very cool. It's very efficient. It builds computational graphs, accumulates intermediate derivatives, uses the chain rules, and so on. And you can also do numerical differentiation. You just do small shifts in your function. You shift it to the left, you shift it to the right, and then you can estimate the derivative from this. That's great. Are these applicable to quantum circuits? And the answer is that generally no. So let me go through all of these options again. Symbolic differentiation cannot be handled by quantum computers. You don't have symbols in quantum computers. This is not how they work. Automatic differentiations, you cannot store intermediate derivatives due to quantum mechanics, basically. So it doesn't work either. Very sad. You can do numerical differentiation. So what you can always do is that you can shift your parameters with a small amount to the left and to the right, and then you estimate the expectation values and calculate the loss function from it, and so on. You go on as usual. But there are problems to this approach. First problem is that near-term quantum devices are noisy. So what do I mean by that? I mean by that the quantum computers which we use today and will be using for the next years are pretty noisy, and we cannot really trust the data which comes out of the quantum device. So we need more resilient differentiation approach. And the second one is that the output is stochastic. So as I mentioned, we estimate the expectation values. We cannot actually calculate them, and that makes that is also another difficulty. Why is it a difficulty? Because if you apply these small shifts, so for example, let's say that you want to compute the derivative at x, then you apply this small shift to the left and to the right, and then you can see that you have many samples here. Usually you have more, but then it is very ambiguous what is like the derivative or the slope here. So this is problematic. So yes, this is very inefficient, because if you apply small differences, then you can imagine that between the samples, each samples, there will be also very small differences. So you have to, if you want to do this, then you have to generally apply more of this parameter shift. That makes usually things better. Okay, but what are parameter shift rules? So in order to avoid this problem, several years ago, parameter shift rules were introduced. These help estimate gradients better in quantum computers. So the formula is very similar to the numerical or the finite difference method, which I have mentioned. But there are some key subtleties here. So this S here is a shift, and it can be large generally, and it is usually large generally in order to make it better. And there is some C constant, but it is not important for now. So it is dependent on the specific gate which you want to apply to. Okay, so the point of this is that the shifts are larger, but the formula is still exact, and it improves the sample efficiency. How is it still exact? I will give you an analogy. So for example, if you have this sine of x function, then you can write the derivative as like a small shift or large shift to the left and a large shift to the right. And you also have this constant multiplier here. And this seemingly the derivative formula is good. So so this is the same with quantum computers, that we shift more and use these kinds of identities. Peter Rakita already told about it, I think. Next question, or the next topic, is continuous variable quantum computing. These parameter shift rules do work in qubit-based quantum computing, or I mean, somewhat work, and but have not been applied or have not been considered in continuous variable quantum computing yet, because it is quite a different beast. What is continuous variable quantum computing compared to qubit-based quantum computing? In qubit-based, you have qubits. Of course, we have talked about this, but in continuous variable CV systems, you have Q modes. I think Peter Kovács already talked about photonic systems. This is exactly the same thing that I'm talking about. In qubit-based systems, you have your Hilbert space dimension. It is finite. In continuous variable systems, it's infinite. The basis states in a qubit is 0 and 1. Continuous variable system 0, 1, 2, 3, and so on. It can go to infinity. You have these elementary gates, which we have been talking about: Hadamard, CNOT, and polygates. And in continuous variable settings, you have quite different gates. I will talk about it. Typical measurements usually do computational or Hadamard basis measurements in qubit-based. You can have more general measurements, but these are the typical ones. In continuous variable, you are restricted to particle number detection. But if we really talk about continuous variable, we are doing homodyne or heterodyne detection. So in a sense, particle number detection might not be considered continuous variable. Anyway, so let's discuss a bit more about this CV quantum computing. in this model, we model the Q modes by quantum harmonic oscillators, and states 0, 1, 2, 3 I mentioned correspond to excitations of these quantum harmonic oscillator. We call them particles usually, and you can see this graph representing these basis states, or like representing their wave function, and yeah, and their energy. And in a sense, qubit-based quantum computation is digital because you have zeros and ones, while CV quantum computation is analog due to these funny wave functions here. Also, these drawings are a bit funny because I drew them, so I didn't manage to quite get it. This is not actually how they look like. So CV quantum states can also be described as quasi-distributions or Wigner functions over the phase space. You don't have to know what it is. This is how they look like. I said quasi-distributions because they can go to negative, not just positive. So these are not probability distributions in the usual sense. But this is what it is. And the reason I'm mentioning it, because I want to introduce linear gates through this phase picture, or this quasi-distribution picture. Roughly speaking, linear gates in this CV quantum computing model are only the squeezing gates, the rotation gate, or phase shifter gates, as they also call it, and the displacement gate. So how do they work? A squeezing gate, what it does, if you start from a circle, this represents a Gaussian distribution, which is uniform at every direction. It squeezes your state into one direction. Typically, it is the position direction, right? And you have rotation or phase shift gates, which is I'm mentioning it that it is particle number preserving. It is not immediately clear why it is, but it preserves the number of excitations in your system. It rotates your, for example, this is a squeeze state, and it rotates your squeeze state with some angle, which is the parameter. And also you have this displacement gate. What it does is that it displaces your little blob with some parameter r. Here it is a negative displacement. Okay, so this is how they work. Can we apply parameter shift rules for CV quantum circuits? That is the big question, and I will tell you the answer later. Of course, yes, but there is some price, and it might not worth it. The parameter shift rules have been applied in photonic quantum computing, or not in CV quantum computing, but in photonic quantum computing so far. It works with linear gates, where no nonlinearities are allowed. Nonlinearities mean that you cannot have nonlinear gates, which I didn't tell you about, but they also exist and are required for universality. And it has been applied recently to particle number preserving linear gates, or in general linear optical quantum circuits, which mean that you have a fixed particle number, and you can do operations on that. And this is not the CV model, obviously, but this method, this particle number preserving method, works with trigonometric interpolation. So here, typically, your expectation values, which I will denote by f, depend on some parameter angle theta. This is the parameter corresponding to a phase shifter or a rotation gate. And it can be shown that this f theta looks like this. So this is like a trigonometric polynomial, right? And it has these ck parameters in there, and generally you cannot compute them. It's really hard to compute them. But what you can do is that you can try to interpolate it. So you take measurements at several different points, and you try to estimate these CK parameters, and then you will have an estimate of this F. And I should mention that this R, this is like the number of frequencies in this trigonometric polynomial, depends linearly with the number of particles in the system. So this is good. And if you have your trigonometric polynomial, you can calculate the derivative. It is very straightforward. And the question is, can we use a similar technique in CV circuit? So can we use it for squeezing gate or displacement gate? And the problem with this is that in the continuous variable setup, the number of particles is usually not fixed. So the previous approach won't work, but we can argue heuristically that the contributions of higher particle numbers are small in usual cases. So what you will see in your function is that there are multiple higher frequency parts there, but the amplitudes of the higher frequencies are generally small. This is of course very heuristic, but the expectation is that if we increase the degree of the trigonometric polynomial, the distance between f and so the f is the function that we want to predict, and f hat is the function that we calculated. So the distance between them will decrease sufficiently fast for optimization purposes. That's the hope, at least. And the observation is that similar strategy would work if we would apply it for the Kerr gate, which is a nonlinear but particle number preserving gate, but we have to increase R. So so we have to square it basically, and this will also work in the original setup as well, without the CV. With outside of the CV model as well. So the question is, how do these expectation values depend on the active linear gates? Sorry, this is a bit technical, but you can show by these recursion formulas that that the displacement gates will have some dependence on this parameter R. So the aim is that we want to somehow determine how the displacement gate depends. Is it a trigonometric polynomial or a polynomial? What is the dependence of the expectation values with respect to R? And that's why we want to calculate the matrix elements of these displacement gates. The problem is that it's an infinite dimensional matrix, so we have to cut it off somehow. And also it's not easy because we have these recursion formulas. But we can show quite easily that if you calculate these kinds of expectation values for a fixed state, fixed initial state, you get this formula, which is almost a polynomial, except for this e to the minus r squared over 2 part. But you can factor it out, and you can interpolate the rest. This is good. So we can interpolate like G hat, which is trying to approximate GR by polynomial interpolation. This can be used, and squeezing it is a bit more tricky because it has a more tricky dependence. It contains these hyperbolic tangent functions, but the statement is that it can be cast into, it is also a polynomial, but you have more polynomials. But the point is that you can still do polynomial interpolation somehow. I won't explain it now. And so far, what we have done is that we have determined the interpolating functions for the squeezing gate. For the rotation gate, we already had it, basically. For the displacement gate, we determined it, and for the Kerr, we use the same as for the rotation, but we we increase the number of frequencies. So we have interpolating polynomials, and from the interpolating polynomials, we can approximate gradients. And this is very important that we include the Kerr gate, because if we use linear gates, so the first three, and the Kerr gate, then that means that we have universality in the continuous variable model, which means that we can have, so if we have a variational quantum circuit consisting of these gates, this can have high expressivity. So it is promising, but numerical simulations show that it may be not worth pursuing this direction. So what I'm meaning here is that the gradients which we estimate are not significantly better, or I mean they are also good, but with finite difference you also get similar results, and it might not be worth pursuing this direction. So I ditched this idea, but we have interpolating polynomials. And can we do something better? And that is when I talked with Peter Rakita at Wigner Research Institute. He was very keen about his project, about line search, and I thought this was a very good idea, and maybe this line search strategy would work in the continuous variable picture as well. Yes. So what do we do? Peter already explained the basic idea, I think. So instead of calculating the gradients, we can use the minima of the interpolating polynomials of the gates. We can, so if we do this optimization, we can sample some parameters, where L is the number of parameters, and then in each step, we of course sample new parameters, and we modify the parameters according to the parameter-wise minimum determined via interpolation. So what is the basic idea? Is that you have this f theta. This is the dependence of the expectation value concerning that particular parameter, for example, corresponding to a rotation gate. And then you can determine the f prime theta, the derivative. That is good. But you can see, I mean, you have the interpolating polynomial. So you have information about the loss landscape along that direction. So why don't you just go here? This is the minimum. So that is the basic idea. 3 minutes. Okay. Okay. We have used this technique for a circle classifier. This is a classification task. I generated an inner circle, an outer circle. They contain each other. And I try to train a quantum circuit, a continuous variable quantum circuit, which learns if I give a new data, which circle does it belong to? That's a really easy task. And I use this circuit. This is a very small circuit, but the problem is that it is very difficult to run larger circuits with continuous variable quantum computing due to the infinite dimensionality of the Hilbert space. I use the very simple mean squared error as a loss function, where I use the expectation values, and the expectation value is the expectation value of this x observable here, which I didn't mention, but I want. It doesn't really matter now. It corresponds to a homodyne detection. And I have run some simulations. So I use the finite difference method with 2 distinct learning rates. And here you can see that I tried with a smaller learning rate. It learned, but slowly. If I adjusted the learning rate to be bigger, then it essentially, reached the minimum or some minimum, and then it jumped back. So seemingly, if I increase the learning rate, it doesn't solve this issue. But with line search, of course, not of course, but the line search immediately found a parameter or found a gate and adjusted it so that it can immediately get close to a minimum. And the point here is that I use very few samples. I mean, much fewer samples here than for the finite difference method. And I also got closer to the minimum faster than the finite difference. So it seems good. It seems promising. I hope it would work for larger systems as well. And I should mention that I used Picasso, which is now published in Quantum for the simulations, and Outlook. This is very heuristic at this point. I didn't work too much on it. We need to determine some guarantees regarding the interpolation error. I didn't check how noise affects the optimization procedure. I should also check it. I should compare with other optimization methods, for example, Fobila, SPSA. We want to generally use MMD or KL divergences as loss functions in quantum machine learning, so we have to adapt this to that. Can we use the approximated gradients in Q-pins, as Peter mentioned? That is a natural question because we are calculating gradients here, and more quality gradients might be better here. Can this help mitigating Barren plateaus? This is the question that Peter Rakete also asked, and you can also ask it here. Thank you for your attention.
Thank you very much, Zoli. So we almost reached the coffee break, but we have time for some short questions, if any.
On the last plot that you showed, I missed how you said where you show the results with the performance. Yeah, here.
Yeah.
So the number of samples, why does it increase with the number of iterations?
Oh, this is the number of total samples so far taken.
So that
yeah.
Every iteration you add, you have the same, you repeat it. Okay.
Yes. Yeah. So basically, this is a constant for the finite difference method, but in the line search method, it's different. It depends on the particular game. So yeah.
Any further questions or remarks? Maybe I have one for this. So what's the reason that it's going down and coming up after?
Oh, because so if the learning rate is too high, then it goes close to a minimum, but the learning rate is still high, so it goes over the minimum.
Okay. So that's a standard thing, yeah.
So that's a standard thing, and that's when you have to decrease the learning rate, basically.
And how it goes, even if you would go to higher number of iterations, then it's goes in parallel, both the finite difference for the lower and the higher values. So here. So if you would go higher, that it goes down in parallel, or?
Yeah, I don't know if they will join. It's not necessary if they join. I imagine that if you would let it run for longer, then both will go to this green, but slower. Basically, that's the point. I didn't have time to.
No, it's not just okay. Thank you. I think let's thanks Zoli again.